Welcome back to OCR MEI Further Mathematics B. Today we're doing chapter 5.6, Maclaurin series. Maclaurin series can be very algebra intensive, and if you can't do it well, then try to break it down into smaller units. So if you have a massive fraction with basically you can see it's a multiple of two components, then do separate out the two components, then do the Maclaurin series on each of them, then do the multiplication afterwards, because most of the time these questions will ask how to express the Maclaurin series of a certain expression as up to the point where you have the power of say 3, then this breaking down method helps a lot. Before I tell you what Maclaurin series is, it is essentially a way of expressing a function f of x or any value such that it is in a polynomial form. So as we know, there are a lot of functions that doesn't have a polynomial, well, you do not know the polynomial of, such as e to the x or sine function or cos function, etc. Technically, they are all polynomials. There are polynomial expressions. There are infinite sums. So the function f(x) can be stated as the function at 0, where x is limited to just very small, approaching 0 value. So this is the Maclaurin series expansion, or also it can be called the Taylor series expansion around the point 0, 0. So if you talk about Maclaurin, then you do not need the expansion around whatever expression. If you're fancy, you want to talk about Taylor series, go ahead. Call it Taylor series, but do note that you need to say it is expanding around 0, 0. Okay, so this is the first term of the polynomial. Then the second term is the differentiated form around 0 multiplied by x. Then you add the second differential around 0, then multiplied by x squared onto factorial. In this case, technically I have 1 factorial here, but it's just 1, so most people don't write it. Then next up you have function 3 differential of 0, x cubed on 3 factorial, etc. up to the point at technically it adds up to infinite. So to express that, we have function of differential n denoted by the power in brackets of the certain power of 0 multiplied by x to the n on n factorial. This is the series expansion up to term n, where n can be any real value larger than 1, technically 0, because you can have only one term. So what this actually means is that all of the differentiable terms or things, expressions, can be expressed in the form of a polynomial. The reason of which is because as we differentiate these terms, given that x is tiny, we can, before differentiating, we can say that f of x around 0 is just f of 0, because these are too small to be accounted for. X is tiny, right? Then after we've differentiated, we are left with this constant goes away, this x disappears because, well, divide by the power drops and you have x to 0, etc. Your constant becomes function differential, first differential of 0, around 0. The rest still got the x terms, which means that they are also too small to be accounted for, and therefore your f dash x, first differential of function x, is just the first differential of function of 0. Yeah, this is a mouthful, but this is essentially the explanation of why this equation takes the form of this. What you really need to know is just this pattern. You can just brute force remember this pattern, to be honest. It's not worth trying to prove it, or to learn how to prove it. It's quite complicated. I wouldn't say it's not doable, but if you're interested, go online and do a tiny Google search. You will find them. But for Maclaurins, there are a lot of standard series that you need to know, standard expressions that you need to know how to express in the Maclaurin series. I will do that in the next video, but this one I'm gonna show you how to actually do one of the Maclaurin series. So I have 1 take x to the power of n. Actually, this is a bad idea. I don't want this n. Let's just put a -1 there. So this would demonstrate how this whole thing works. So first of all, this is, let's call it function of g of x. So in order to express everything in the polynomial form up to power of 3, let's say, up to x squared. So what I can do here is to, first of all, we know f of x, and so f of 0 is just 1. We have g dash x equals to, drop the power, -1 times -1, chain rule, so that's +1, multiplied by the original fraction, 1 take x to the -2 this time. This one for x is 0 give me also 1 plus 1. Then we have g double dash gives me, differentiate this expression, we have -2 times -1 times 1 take x to the power -3 gives me 2 for x is 0. Let's see, we have 0, 1, 2, we have all these, the 3 terms necessary. So now just express, so 1 take x to the power -1 is roughly equal to 1. Just drop this up. Then we have this plus 1 lot of x, then we have 2 plus 2 lots of x squared on 2, which is just x squared, etc., but we're only expanding up to the power 2. So we have 1 plus x squared plus x cubed, etc. Relatively straightforward, I'd say. If I have yet another expression, let's say e to the x, then we have, let's see, that is 1 plus x squared on 2 plus x on 6, etc. But if I want to find the Maclaurin series expansion of e to the x times 1 take x to minus 1, then what I need to do is to take the first 3 terms multiplied by the first 3 terms of these two. So what I've said, separate these two out as 2 separate Maclaurins, expand them independently, then multiplying them algebraically. That would work much better than if you just differentiate this mess, because again, the algebra gets out of hand very fast, and it's not worth the trouble. So what you do up to power 2, so make sure you don't multiply x squared by x squared on 2, because that's just out of range. So what you would have is 1 plus x squared plus x squared, and that's it up to power 2, which is 1 plus 2x plus 2x squared. So that would be the expression of e to the x 1 take x to the power minus 1. So it's again relatively straightforward as long as you don't make algebraic mistakes. And again, I do not guarantee I didn't do algebraic mistake here, so the point is to teach you how to do Maclaurin, not that I need to be perfect, right? But I'll try to be perfect. I think this should be right. So for the tips, make sure you do your practice, and also check your algebra after you've done your questions, because again, it's very easy to make silly mistakes. So to be honest, there aren't much about Maclaurins in exams. I'm pretty sure there will be 1 or 2 questions based around it in the section A old spec, that is. The new spec paper, I have no idea how they are structured. So yeah, basically I think you should be fine with you will probably be given an expression of which you need to express it in Maclaurin with either 4 terms, first 4 terms, or who knows, sometimes up to power 4. So make sure you read the question about how far you're supposed to get to, and also if you can separate or split different algebraic terms, then do the series expansion separately, then it can help you a lot, because some product rule expansions do give you exponentially many terms. So when you get up to power 4, you might have 7 terms on your sheet of paper, which means that you're basically stuck with a massive mess of algebra that you have no clue how to eliminate your errors from. So yeah, basically that's all the tips I can give, and I will give you some questions to do in a little bit. There we go. So we have 3 questions right here. Give these a thought. Not feeling too well today. So yes, so question 1, take it with a pinch of salt. Question 2, give it a think. It can be, I don't know, there are 2 ways of doing this question, and I'm not sure which way is faster, to be honest. And question 3, standard, very, very standard. And it's one of the standard Maclaurin series that you need to know, or you will be given. So yeah, these will be good practice for you, and I will show you the answer in 5, 4, 3, 2, 1. The answer is shown right here. So question 1, again, take it with a pinch of salt. It is already an algebraic expression. Or not algebraic, but I mean polynomial expression, so there's no meaning to the Maclaurin series of it. So yeah, basically that's the same as the question. Question 2, 2 different ways. Sine cos is, you can do it by product rule, expand, or you can turn it into half of sine 2x. Both ways works. I think I would prefer the sine 2x method because you differentiate less in total. And for question 3, standard, very, very standard, so nothing much to talk about. Other than these, this will be the end of this video. I hope you've learned something. If you have any questions regarding Maclaurin series, do let me know in the comment section below. For now, thanks for watching, and I will see you on my next one.